Hello and welcome to this video. In this video we're going to start the topic of circular motion. So up till this point in AS we would have only looked at linear motion, so things moving in a straight line. We would have looked at projectile motion in some cases where we have some change in direction, but we have never actually seen anything move just completely in a circle. But this comes up all the time in real life. We have loads of things that just move in a circle or follow a somewhat circular path. Whenever you go around a roundabout in your car, you're following circular motion. If you were on a swing, you're partially going through a circular path, so you'll have some circular motion at that point. So because we see all of this, all of these cases of circular motion, we have to come up with a physicsy way of explaining why does everything happen the way it happens, the way we expect it to happen. So we can relate a lot of the properties of linear motion in terms of circular motion, except instead of looking at things like distance, we're now going to look at things like angle. So if we were to think about linear motion for a second, so the linear side will be this side, and then we'll put circular on this side. And this is going to be what the linear motion corresponds to in the circular case. In this case, in linear motion, we'd be looking at a distance that we're traveling. So we'd say that has traveled 5 meters and so on. Whereas in the circular case, we're going to look at the angle that we've actually displaced in that time. So we're going to say that in maybe 3 seconds, it's gone through an angle of 3 radians. Okay, if you're unfamiliar with radians, I would first make sure you're familiar with radians. Go back and look at the waves topic from AS. You should be familiar with radians from there. But if you're not completely happy and you're not like on top of radians, definitely go through radians before you look at these topics, because all of your angular displacements that we're going to measure will always be in radians. Okay, so distance is now changed into an angle. That means we can no longer say that the velocity is distance over time. We now have to say that we have some sort of angular velocity. So before we said the velocity is distance over time, but now we're going to say angular velocity, which we're going to refer to with this omega. So this is angular velocity. And sometimes we'll also hear it referred to as angular frequency, and we'll see why in a second. And that's going to be the angle over a certain time, okay? And we'll find that we can have acceleration, and we're going to refer to this as just linear acceleration, and that is going to become centripetal acceleration, which we probably won't go through in this video, but that will be the next video. So centripetal acceleration, and the same for force. We have a force, and we're going to end up with some sort of centripetal force. Okay, and you'll find that most of the things that we're going to look at are always going to be in terms of this list of variables. So it's completely analogous to the way we did everything in terms of linear motion. We're now just going to redefine a few things so that we can treat things as circles. Okay, so the first thing I want to go through then is how do things change now that we have this relationship of angular velocity. So now let's look at this idea of angular velocity. So angular velocity, when we look at this, we already have one definition of it, but I would say this definition, I haven't put it in a box because this is not on your formula sheet. While this is, I recommend, a useful definition of angular velocity, it's not actually the angular velocity that you'll be given on your formula sheet. Instead, we have a few different expressions for that. Now we know if we're going to go around a circle that we know there are 2 pi radians in a circle. Okay, so if I were to go around the full set, I would have 2 pi. Now we're going to look at one circle as one oscillation. So in order to get from this point around to get straight back to the same point, that's going to take the time t, which is the period of oscillation. Okay, exactly the same as it was in waves, because we're now going to you'll see that a lot of the motion that we start to see now will resemble what we did in waves. So that means that if we know the full angle that it's going to travel through, in the time, then we can redefine the angular displacement as the total angle of 2 pi divided by the time it takes for it to travel around one circle. Now this is your definition of angular velocity, and that means that since we know from waves that 1 over t is the same as f, this is why we can also refer to it as angular frequency, because it's either an angular displacement over time or it's just frequency times by 2 pi to make it angular. Okay, now this is your general definition of this. And as we've said over here, but not explicitly written, this angular velocity, the units of this angle is going to be radians, and this is per unit time, so we usually measure these in radians per second. Okay, so now we have a definition of angular velocity. So if we have something moving in a circle, we can use angular velocity to describe how quickly is it oscillating or how quickly is it moving around that circle. But we can also translate that into some sort of linear motion, since if we have something moving in a circle, we can define a few things about it. We know that we could potentially have a constant velocity of this thing, and let's say we have, for example, a yo-yo on a string, and there's someone at the center of this that is just holding this string, and they're just spinning this yo-yo around, so that its velocity is always going to be tangential. So this is another property of circular motion, is that velocity is always tangential to the path. So in this case, we're going to spin around this direction, but this velocity is always going to be, if I had a particle here, it would go off on a tangent here. If I had a particle here, it go off in a tangent there. So the velocity is always going to be tangential, and we'll find that if the velocity is always tangential, we're going to get a constant change in the velocity, since the velocity is a vector, which means if we have a change in velocity and this has taken place over some time, we have an acceleration. So even if we're traveling at a constant velocity, we can end up with an acceleration. So how do we get rid of or how do we change from linear variables in terms of the velocity that it's traveling at to an angular variable? Well, most of the time we can have this radius, and it will usually be kind of a bridge between linear and angular displacement. For those of you who are going to do engineering physics as your option, at the end of year, you'll learn about a moment of inertia, and you'll come back to this and see that this is actually going to get a little bit more complicated when you have moment of inertia. Or for most people, you'll probably find it a little bit simpler as long as you can wrap your head around the moment of inertia. Okay, so this velocity is going to constantly change, and actually we can have a second definition of this, which is the velocity which it's traveling at, linear velocity, divided by the radius of the velocity. Okay, because what this means is that we have units of meters per second divided by meters, so that meters will cancel. You'll get units of just per second, which is the same as hertz, and since this can be an angular frequency, this expression is correct. Okay, so now we have expressions for the angular frequency, or the angular velocity, so how quickly this thing is moving around this circle, and we can express that either in terms of the angle and the time, the frequency, or as a ratio of the velocity to the radius of that circle. Now, most of the time when we're actually looking at these calculations, like I say, we want to get these units in radians per second because this is when they're most useful, but it's not always the case that they will be given to you in radians per second. So let's have a look at how we're going to convert from from revolutions per minute, which is another unit that we could use, to radians per second. Okay, so let's, for example, say we have a bike wheel, and this bike wheel has one of those reflecting pads on it that is going to continue to spin, and let's say it completes 200 revolutions per minute. the question is asking us what is the angular frequency in radians per second. Okay, so what we're going to have to first do is realize that if we have one revolution, that means we're going around this whole thing once. And so we have to express that in terms of the angle that we've actually gone through. So that means that we have one revolution is the same as 2 pi radians. Okay, so now we can say that if we're doing 200 revolutions, that's the same as 400 pi radians, since we're just going to times this by 200 on this side. So we're also going to have to times this by 200 on this side. And then the time that it's taken, we're starting with 1 minute. We obviously want that in seconds. That's the same as 60 seconds. Therefore, we can write that the angular frequency is 400 pi radians per 60 seconds. Now we can simplify that to 40 pi over 6, and we could even simplify that to 20 pi over 3 radians per second. So this is a very common type of question that they can ask you, and usually for all of the calculations that we're going to do in the following videos, where we're going to encounter things like centripetal acceleration and centripetal force, we always want to have this value of omega in radians per second, because that's how all of these equations were formulated based on those units. So to recap what you definitely need to take away from this video, I would say to understand that circular motion is just an alternate representation of linear motion. So most of the laws and stuff that you already know about linear motion, we can apply those to circular motion just by changing a few variables. In the case of this video, we've looked at velocity as distance over time. We translated that into angular velocity is now angular displacement over time. We came up with 3 definitions for that. 2 of them were pretty similar in terms of the angle and the time, but we defined then that the angular velocity could also be written as the linear velocity divided by the radius of that circle that it's traveling around. And the final thing that I need to make sure that is clear, angular velocity, just like linear velocity, is a vector. Okay, so let's just make a note of this. This is a vector, which means what we're calculating here is only the magnitude. Okay, we're not actually calculating the direction that it's moving in. In most questions, they won't ask you the direction it's moving in, but you should be able to tell them that because it's a velocity, it has to be a vector. We haven't specified what direction these things have to go in, which means you could have both a positive or a negative angular velocity, depending on how you set up your axes. Okay, thank you for watching.